Once again, good morning to to every one of us. My name is Dr. Shegun Oke, and then I'll be facilitating this module, as I said last week, and we continue from where we stopped. Then I would like to share my screen for some of us to see some of those stuff that we have this morning. But before then, let me call our attention to this. Can you see my screen, please?
Yes, sir.
Can you see it?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay. Let's move on. From this, thank you for seeing it. When we call linear transformation, just to quickly tell us why it is important to have all this in view. When we call linear transformation, there are so many things that are involved in linear transformation. And one of it is what we are about to witness now. So here we have what we call a linear transformation. Is a function of t that maps a vector space V into another vector space. So, for example, we have it in this place, as you can see here, that V is the domain. What do we mean by domain? I will explain by illustration so that some of us that were used to 1 + 1, 2 + 2, we also understand what a domain is in a layman language, although we might not be talking in a layman language all the time, but at least to tell us that we are not in total abstracts, I would like to explain in a simple language to some of us. So if you look at it, domain is this big bracket. We call it this. We have this as our domain. Now, we have a point here, which move from here to another space. Then there is this particular space inside. I will explain it later. So at this point, if this man mapped to this one, which we call our T, which is transformation, and we have here, we have our small phi, and we have our small w. Our capital V is what we call our domain. This is our domain. I'm just trying to explain this, and which our capital W is our codomain. Now, what does this mean in a real sense? They are very simple. It simply means we also call the capital V, we call the small omegas, that is the small w, we call it another name. Some people can say, oh, what do we call this particular one? I will explain. It simply means, for example, in your place where you are now, I can ask you to draw something and you will now explain it to me. And once I call you, get ready to talk. For example, I have this. Let me give us this, a small one.
Sorry, sir. Some people's mic are on and it's distracting.
Okay. Please let us mute ourselves. If I unshare this, let me just, if I unshare this and we discover that you are the one disturbing us, I will remove you from the class and you will not be able to join again. Please mute yourself. Thank you. Let us respect that. It is a very simple thing. Except if you want me to, I will use another setup for you. Yes. Afolabi, raise up your hand. What happened? Okay, let's proceed. So in this content, there is something we need to show us. Okay, let me just try and insert the table for us. Okay, let's continue with the draw. I will just explain because this is not the note for today, but I'm just trying to explain. Okay, what I'm saying is this. For example, in my own case, I can take it this way. Let me say, this is my domain. My domain is 1, 2, 3, 4. Don't forget what I call it, domain. My domain is this. So if I want to explain it in a better way, I need to clean some of those things here. So if I want to explain it in a better way, I can have at this point, this is my A. Let me call this one A. My B is 1, 2, 3, 4. 5, 6, 7, 8. Let me just continue here. Okay, for those of us that have the pen, you have your book with you. Do me a favor, write on your notes at this stage. You know, I have, write the one of A, call it a domain. The one of B, call it a codomain. Codomain. Label it from 1 to, let it be 1 to 9. Okay, we have 1 to 9 here. According to the 1 to 9, how do I know? And the question says, let your X map to 2x plus 1. Let X map to 2x plus 1. My X are let's say my x in A, map to 2x plus 1, meaning that when x is 1, what is the capital X will be? Okay, let me call this one capital X so that we will not miss. When I'm mentioning X, you will understand what I'm saying. So when X is equals to 1, you know my 1 will map what? My 1 will map 3.
3.
Yes. Then when x is equals to 2, what happened?
5. F, we are map 5.
Is what?
It will map 5.
5.
X, we are map 5.
When x is equals to 3?
7.
7. When x is equals to 4?
It will mark 7. 9.
9.
Now, the question now is this. You know those ones that he mapped outside, let's call them out. This is what they call codomi. This is what they call range. Call it range, or they call it image. They call it range, or they call it image. Don't forget, they are coming out from where? From the domain. So, according to the definition of the domain and codomain now, you can see from this graph that you can see here that from here, let me use my highlighter to be able to. You can see from here, it maps this. It's not all the codomain it maps, but a portion of codomain. So now, let me tell you the application of this. For some of us that were in medical line, or for some of us that were in military or paramilitary, or for some of us that you work as a system analyst. Now, if they want you to code something, or you are working in hospital, how do I apply this? That is why you see mathematics is the bedrock of everything. A whole of our body is what we call domain. Now, a portion that is sick, let's say the person has a cancer of the lungs, they will not heal the whole body. They will be looking at the range. Where does the cancer located? That is our application of mathematics to the medical line. Mathematically, it will give us the opportunity to know that, okay, we need to trace, let's map it out. So that they cannot just, medical doctor will not just enter theater and be cutting anywhere. No, they will rather locate that particular point. After the location, they will now be mapping it. What leads to this? Now, for example, the issue of military. If the military want to control maybe a chaos or a riot in a particular geographical area, they will not kill everybody in that place. Don't forget. Can you hear me now? Are we together?
Yes, sir.
Yes, sir.
Yes, sir.
We are following.
Yes, sir.
So what they do most times is just to locate a particular point, the site where the problem lies. So that is the application of mathematics. Now, let's move on. We have what we call axiom, the two axioms of linear transformation. That is, where anytime you have this, when you have t plus, in bracket, u plus v, so we have it to be t, we have our t here, okay. we have our T. We all know the T to be our transformation. So when we have T of U plus V, it simply means it's the same thing as T of U plus T of V. For all V, this symbol means for all. For all U, comma V, that belongs to the capital V. That is, they are all they all belong to this capital V. So if you can show any problem, they want you to prove that this particular question is linear transformation. You must be able to show this. And number two, that's why I said definition in this case, they are the key. Number two, you need to show, this is number one, you must show. Number two is to show that T of C, U, is the same thing as our C outside. That is, let's say it's a real number. It's not a complex C. So we have it to be U. And for all C that belongs to a real number. So let's take note of that. So if you can know this definition, then look at the image I just explained. Look at the range of T that also belong to V. So, but let's look at this. Note, a linear transformation is said to be operation preserving if all these condition holds. This is scalar multiplied by our omega, our W. And this is addition, if you can show the addition, and you can show the one of scalar multiplying by our V. So then anytime the linear transformation, that is V mapped to V, that is a map to itself, is called linear operator. Anytime it happens, it's called linear operator. But in this case now, we want to verify. We want to verify that a linear transformation T from R of 2 is a linear transformation. Then we have this. Moses, raise up your hand. Any question?
Yes, sir. I think you are rushing it, sir. The note that was upward. Can you just go back or let us, because I'm copying notes now, sir.
You are copying the note. Don't worry. You will have the record. Remember, this class is 1 hour. You will have the record.
Okay,
As a matter of fact, I'm just trying to take it easy. We are not to see. We are just to facilitate.
Okay, sir.
But I noticed from our faces expression that some of us are not finding it easy. Yes. So some of us are not finding it easy. So you can lower your hands. Don't worry. Everything is in course material. I'm just trying to make it simpler so that all of us can be carried along. Let me just prove this for us. And from the proof, it is very simple that we have this. But this particular one you are looking at, Musa Abdul Idris.
Yes, sir. Please, sir, I want to beg, maybe after the lecture, can you post this very note for us so that we can go through and refresh our brain?
Unfortunately, I will not release this one for now because there are part of them that we will not be able to touch. I have a lot of slides I'm going to give you, don't worry, but not now. Why I'm saying not now is because I don't want you to be confused. Be using the course material, but I will still release it, but not immediately until I finish this particular slide. Because from the experience, some students will just copy, we just take the slide and they won't come to class. Don't worry, I'm going to release it, but I will advise you write when you are there. Watch the video later and also write. It will help you. is what you write that stick, not what you watch. This is not Nollywood. Please, guys, we just have to write it down. That is the beauty of mathematics. So don't worry, sir. Thank you.
Thank you, sir.
So linear transformation T is from R of 2 into R2. Now, what does this mean? They already give you that we are working in a space of 2. So what we need to do is just to try as much as possible to work with that. So, which means that, let me just try and let me share another one, okay? So that where I can write conveniently for you guys. So at this point, what it simply means is we need to show that, number one, we know from the question says T V1, V2 is the same thing as our V1 minus V2.
So we are not seeing it on the screen.
Oh, okay.
So we can't see anything on the board again. No.
Okay.
It's not showing.
Don't worry. Resume share.
All is blank.
Can you see now?
Yes, sir.
Yes, sir. Yes, sir. We can see now.
You can see. Okay, I will reshare it. Don't worry. Can you see?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now, I'm trying to solve this again. Then we have V1 plus 2V2. So for us to prove this, that we need to show that it is linear transformation. Don't forget the two axioms that I've explained initially. We need to use them. Addition. We need to do the addition first. For us to do the addition, let's say vector addition. Nobody will tell you to show vector addition first, but you yourself will know from the definition you memorize or you know from day one. So to show that U plus V, we need to first of all show U plus V. But before then, let's define this, because people will ask you, some people will ask, where do you see U now? U is not part of it from day one. Let me erase it so that you will understand from where I'm coming from. Okay, let's say, let's U equals to U1, comma, U2. The question is, how do I know? But I know, I'm aware of this from my definition. Definition says T into U plus V. But the question here is just giving me V. But I know from the definition that I need to introduce the U. That's why you can see. I said let U equals to U1, comma, U, comma, U2. U1, comma, U2. And my V equals to V1, comma, V2. They are all in real 2. They are all in real 2. And don't forget, my C can also be any real number. My C can be any real number. So let me move on by saying, since I know my factor, then I will now start with the one of addition will be U plus v. My u plus v will be in bracket u1, comma, u2 plus v1, comma, v2, which is the same thing as u1 plus v1, that is all the one will be together, then all the two will also be together. So from there, I can now introduce the transformation. I can now say my t of u plus v is the same thing as t in brackets u1 plus v1, comma, u2 plus v2 together. Don't forget the question. You need to go back to the question. The question says, this is the question says, t v1, comma, v2 is the same thing as v1 minus v2, comma, v1 plus 2v2. So, meaning there are places whereby you will see 2 in the question, in the solution. By the time I'm substituting them back now, you will see what I'm trying to explain to you. So I'm going to have this. I'm going to have in brackets u1 plus v1 minus u2 plus v2, comma. Then the next thing will be u1 plus v1 plus, sorry, so we have it to be plus 2 into u2 plus v2, close the big brackets. Then by the time you begin to separate them here and there, at the end of the day, you have, if you work it very well, you're going to have something similar like this. u1 minus u2 plus v1 minus v2. Then your comma is there. Remember, you are working with in 2. If it is in 3 space, you have 1, 2, 3. If it is in 4 space, you have 1, 2, 3, 4. So this is 2. So that's why you see u1, u2. Then we'll move on by saying the next time we have here, we have u1, sorry, you raise up your hand. What's the question, please?
Yes, my question is, if the concept is explained using numbers first before it's applied in solving it as an example like this, even we can also solve it as you are solving it here.
But so remember, you are not going to
the concept.
That's why they call it algebra. They did call it calculus. You get my point, sir?
Yes, sir.
I'm only making it simple. If you check your course material, you might not see something similar here. But I'm just trying to look for simpler way of explaining or make it simple so that you will not see it as that bad as abstract as we think. Nobody will. If you check the YouTube video, it's more or less the same thing. Nobody will explain it more than this, they will also make it complex. They will just read it for you and they will go. And that is the way the course is being designed. They are not the one that is that okay?
Okay, sir. But if we say linear transformation, what are we transforming from what space to what space, and what are the rudiments of the transformation?
The rudiment of the transformation is for you first, know the property, know the definition. Is that okay? Just make sure you know we are using the definition now to show something is linearly transformed. Is that okay? So once you can prove the two axioms, that means the whole properties and the question is transformation, is linearly transformation. It can be linearly transformed. So that is the essence. It's not because you are moving from, we say, to Gariki. No. They are not saying you are moving from one space to the other now. But in this case now, the question does not ask us to move from one space to another. So, and let me quickly say this. It might not make sense to you, but some of us that still have the mind to go further in our studies, you will appreciate it by the time you begin to apply it to the. So as for now, let's continue in this manner. So you can agree with me that all the U's are being together while all the V's are being together in additional manner. So I can now say, therefore, my T of U, according to the definition. Remember the definition says, if you remember from the one I showed you the other time, our definition is the same thing as U plus V is the same thing as T of U plus T of V. Therefore, which implies that we already achieved that from up. We can say that we have T of U1 minus U2 T of U1 minus U2, comma, U1 plus 2U2 plus T of V1 minus V2, comma, V1 plus 2V2. So this, so you first, that is the addition. Then the one of scalar, you have to do this one of scalar too. Then the one of scalar says, here is the scalar multiplication. Scalar multiplication says, one of scalar multiplication says CU is the same thing as C in brackets U1, comma U2, which is the same thing as CU1, comma CU2. Then for us,
if I don't load a film, I open and where?
Who is this person? So it's the same thing as T into CU, which is the same thing as T in brackets CU1, comma CU2. So I can now open it by saying, we know the CU1, we know the question we're given up. So the same question will be transformed to be CU1 minus CU2, comma, then CU1 plus 2CU2. Remember, you have to factorize the scalar out. Our C will come out, we have U1 minus U2, comma, then U1 plus 2U2. Therefore, we have C to be TCU. That is, it implies that our T is a linear transformation. Any question? So please, let's take note of all these axioms, definitions, and some other things we need to know. But according to the properties of linear transformation, as I explained the other time, let's quickly check the properties. So maybe that one will also help us. The property of LT. Anytime I put LT, it means linear transformation. So the properties says, let's say our T such that V map to our, that is domain, map to codomain, which belongs to our U, comma V, they all belongs to our domain. Therefore, one of the properties says, number one property says, probability 1 says, T of 0 is equals to 0. Take note of that. Number 2 says, T of minus V is the same thing as minus T of V. Take note of that. Number 3 says, T of U minus V is the same thing as T of U, like I will solve it now, minus T of V. Please, let's take note of that. Then the fourth says, if Idris, that's the last chance for you, please. I'm going to remove you from this platform, and that's the head. If V is equals to C1 V1 plus C2 V2 plus dot dot to Cn Vn, you can say that.
Let's say from the properties.
Yes. C1, C of V1 plus C2, T of V2, Cn, T of Vn. So what this is saying is that, don't forget, before I put this one, this has already come. We already introduced our T. At this point, we already introduced our T. We already introduced T of V already, which says T in bracket C1 V1 plus C2 V2, plus Cn Vn. So this particular one leads to this. It leads to this one.
Sir, help us adjust the board. We are not seeing it clearly, sir.
Okay, sorry. Can we see now?
So let's see the property from up.
Is it okay now?
Sir, adjust it. It
The
has
writing is
gone
blocked,
back.
sir. Blocked.
It has gone back to where it was before.
Is it okay? Can you just see it? Yeah.
No, sir.
No, it has gone too down for me to see.
Oh, okay. Check your course material, they are all there. I'm just giving you the summary of what I want you to lay emphasis on so that we can see all together.
This part is clear, sir.
It's clear.
I like this part. The only thing that I want to suggest is the writing of letter U should be different from V. They look alike.
But that is why you are in class. Immediately you are following my mouth. Please be jotting it as you. That's why I call it. Don't forget, I'm using, not all the lecturers have the material that I'm using to write. Some of them will just write in the paper, and which I don't, to me, it's not convenient. I can write in paper and scan it and send it to you, but it doesn't make sense. What's the difference between I write it in the paper and scan it to you when I cannot participate? So please bear with me because of the what I'm using. I have to just get a smart board to write. Unfortunately, let's just manage what we have for now. Don't worry. If you send the touchscreen laptop to me, I'll be using touchscreen laptop for you. So you will see it as if you are in the board. Just send it to me. We will be working on it.
No problem, anyway, sir. We are following, sir.
Okay. Let's look at the examples. I'll just give us one of the simple examples. The example says, when you have, let's say example 1, says, let T be in space of 3. Don't forget, space of 3. Be a linear transformation, LT, like I said, such that.
Sorry, sir. Is this space of 3 something like 3 dimension?
Yeah, is in 3 form, like X-man, S2, S3. You see, yeah, like the one up now is in n dimension. That is in n form. So the one of 3 will be, meaning that I'm working in the real space of 3 space, in a 3 dimension. So such that I have what we call the T of 1, 0, 0, which is the same thing, which is equals to 2, minus 1, 4. Then I have another T, which is another space, 0, 1, 0 is the same thing as 1, 5, minus 2. Then I have another one, which make it 3, 0, 0, 1 is the same thing as 0, 3, 1. The question says, find T into 2, 3, minus 2. Find 3 into 2, 3, minus 2. How do I go about this? In case I'm given this type in the exam or in the test. So it's very simple. What you need to do is, let's solve it. Solution will be, remember, I'm to look for 2, 3, minus 2. Then, which is the same thing as, for this first space, 1, I'm going to have 2, which is the first element, in brackets, 2, minus 1, 4. Any question? Do you understand what I'm doing? Then yes, the next one, yes, the sign is positive, right? 3 in brackets. But don't let me write it this way so that it won't look confusing. Let me just try and clean this place. It's still the same thing, but just hold on. Some of us might not be able to capture what we're doing straight away. So what we're saying is comma 1, 0, comma 0. Then the second one will be second phase, which is going to be 0, comma 1, comma 0. And the third one will be, you see, the third one is negative, minus 2 in brackets, 0, comma 0, comma 1.
So your board has adjusted, sir.
Yes, I did that just for you to see. Can you see?
I'm not seeing it well.
Just see the correct one that I'm writing is the word that matters, not the one I've written.
We are saying it.
Is the one that I'm writing first because of the space. Don't worry, you will see everything. Just copy the one. If you are writing, you can write the one I'm writing now. So I'm the one adjusting it from here. So that the board will contain it. Now it will be now 2 in brackets. What is for t? The first t will be what? 2, comma minus 1, comma 4.
4, yes.
Plus 3 in bracket. What is the second space?
1, comma 5, comma minus 2.
Minus 2.
Then the third space is what?
Minus 2.
Minus 2 in bracket.
0,
0, 3, comma 1.
Now, how do we solve it? We need to now multiply it. Now, you have to be careful here. Note that this is S1 for space 1, S2, S3. I just try to distinguish it. X1, S2, S3. X1, S2, S3. So what it simply means is we need to multiply all the X1 with their coefficients. Meaning 2 in bracket 2 plus 3 in bracket 1 plus, is it plus now?
Minus.
Yes, thank you. So it's going to be what?
Minus
2 in bracket what?
0.
That is for all X1. So, comma, what is S2? The one of S2 will be 2 in bracket what?
Negative
1. Minus 1. Plus 3 in bracket what?
5.
Then minus 2 in bracket
3.
That is all for S2. Then you do the same thing for S3. I will adjust the board again. So it's going to be what?
2 in bracket
4.
2 in bracket 4
plus 3 in
bracket what?
Minus 2.
Minus 2 in bracket 1.
Minus 1.
So what's the answer for each of them?
4 7 7 0.
Thank you.
That's 7.
Final answer will be 7 7 0. If you do it very well.
Wow.
Yeah, 770.
770. So that is just you do it very well, you have that. But if you don't do it very well, you'll still be struggling. So if I ask you now, I can ask you to find, from figure 1, t into minus 4, 5, 1. I ask you to find it using the same method. You will see you have different answer. So that is, by the way, our time is fast spent, but let me quickly show us. Please, I want you to go and master some of those proof, some of those theorem in your book, so that you will not say that I don't want to bug you with that. Then maybe as time goes on, I'll try and do some video. Then I'll share the link on the WhatsApp group. For those of you that are interested, I will explain some of the proof there and some of the theorems. Then you can also make use of them. But there are cogent proof that says,
Yes, sir.
Yes.
Can the values be written vertically, each of the x, then compute the final answer and then write it like you have really done now?
It all depends on you. Just give us the final answer. That's just the answer. I'm just using this period, this particular one, to explain this area. I'm not supposed to write it this way. You guys are not in primary school. I'm not supposed to write it in this way. I just use it to explain to you, so that you won't see that this guy is doing abracadabra. Is that okay? So you can check. If you check the manual, you see that it is not that easy that way. I just look for the examples just so that you guys will be able to familiarize yourself with what is really happening. But let's quickly solve this, and I will show us an example, then we call it a day. Is it okay by us?
Yes, sir.
Okay,
Yes,
theorem. For theorem, let me say theorem of this. We said let's T such that V map to our W. In your manual, they use U and V most times. So it's still the same thing. Be a linear transformation. Be a linear transformation from an n dimension, from an n-dimensional, let me put it that way, from n dimensional vector space. Dimensional vector space. For n-dimensional vector space V into a vector space W. Then our rank of T plus nullity of T is equals to N. Don't forget this definition. They are very important. That is dimension of, we all know what it means, range of T plus dimension. We did kernel last time. Kernel of T is equals to dimension to me of T. The domain of T. That is, I will show us a very simple example in this contents. Then you will enjoy what it means. Proof. The proof of this is very simple. I've seen it in the questions before. They ask you to prove it. Some of rank and loyalty. So please take note of that. Let T is represented. T or presented, let's say presented by a matrix. By a matrix A, N, M, subscripts A, N, M, that is row and column. Assume our rank A, assume our rank A is equals to small r. Now, we need to prove Roman figure 1 now. The Roman figure 1 says the rank Roman figure 1 says rank of A, oh sorry, for the A now we have the T first. The rank of T is equals to the dimension of range of T, which is the same thing as the dim, that is dimension of column the column space of A. We are still talking about the rank of A equals to R, which implies.
Sorry, sir.
Yes.
Can I say that the column space of A means the number of columns of matrix A?
Can you repeat yourself, please?
Okay, what I'm asking is that you wrote dimension column space of A. Should that also mean the number of columns of matrix A?
Mm-hmm. Yes, the dimension of columns of A, should you say is the number of column A, all right?
I'm just asking, can it mean the number of columns in matrix A?
Sure. You will see the example. Don't worry. But by the time we get there, I will give us one simple example. Then from then we call it a day. It's just one line or two lines. You know, when you say dimension, it simply means how many number of columns do you have, right? So from there, you can now pick it up.
Okay, sir.
Okay, now we have, then on this case now, where we have the D, this implies that T of X is the same thing as a matrix of A of X. So from there we have matrix A, we have rank of A. Then number 2, the point 2 to show is nullity of T is the same thing as the dim of kernel T is the same thing as the dim into solution space of A. which implies that n minus r. That is, by the time you take it to the other side, it will now equals to r, the rank, t, plus the nullity of t, equals to r plus n minus r, which is equals to n. That is, at the end of the day, by the time you open the bracket, you discover that it's the n that remains. But for this case now, let me give us an example of one of the examples that I want to share with us is, let's say, we have a matrix of m, n, that is m by n matrix. Let me put it this way, m by n matrix, which we now have it to be our rank of A in this context to be plus nu t A to be equals to n. So if I have 5 by 4 matrix, I say A equals to 1, 2, 0, 2, 1. Then here we have 0, 1, 1, minus 1, 0. Here you have 0, 0, 0, 1, 1. So the last phase 0, 0, 0, 0, 0. So how many columns do we have in this case?
5 columns.
So
and 4 rows.
So you can see this is
4 rows.
Some of us say how many? Column 1?
5 columns and 4 rows.
Column 3, please. This thing is very important. Column 4, and you must know it, which is column 5. So that's not the way, that's not where we are going. I just want to, and we have 4 columns, we have 4 rows. That is, we have it to be 5 by 4. So what is the rank of this A? Anybody? The rank of
the rank
A.
is 5.
The rank is 5. Really? Okay. No. Okay, don't let me ask for rank first. What is n in this case? N. Because remember your proof equals to n. This is the definition you need to solve. You need to use to solve them.
2.
Hello, yes, it's 2.
N is 2, right?
Yes.
That's good. How do you solve it? Where do you get n to be 2?
Because 2 is the highest number there.
No. Let's go back to the definition. They said rank of T plus nullity of T equals to n. We are not talking about the number of the matrix. And what is n from the proof here? We are talking about nullity. And the definition for nullity is dimension of domain of T. Don't forget, dimension of domain of T. So dimension of, what is the dimension of this matrix?
It's 4 by 5.
And we know it's 4 by 5. The dimension we are talking about column. How many columns? Is 5.
5.
Remember his dimension. The man that asked question the other time, Ola Deborah, what's your name, sir? So it's 5. So Then the rank, that's where we have rank. Rank of A in this case will be what? Let's look at the diagonal method. We have 0, we have 3, we have another one here.
Okay.
Right?
5.
Sir, we can't see your board, sir. We can't see your board, sir.
Why? Can you see the board, sir?
Yes.
We can see it.
Oh.
So, okay, let me try and clean the matrix so that, let me clean this so that you can see. I only use that one to explain. Okay, let's back to the matrix itself. Can we all see it now?
Yes.
Yes, sir.
Okay, so if you look at the diagonal elements, some of them are 1.
Some of
We
them.
have 1. The last one is 0. So that is what you use to rank it. That's where the ranking come in. It's not the ranking of normal metrics that we normally do in this case. Remember, we are trying to look for rank of A, and the whole A is the matrix. So the rank at this point, the rank is 3.
Sorry, sir, because this matrix is not a square matrix. The diagonal we don't have a main diagonals, and we have so many diagonals. Which of the diagonals are we using to determine the rank?
Now, since it's not a square matrix, it's not the one of, go and read the definition of rank first. I think I mentioned it somewhere.
Yes.
Yeah, go and check the definition of rank in the first slide and see how do we define the rank in this content. The rank we are talking about in this content is not the issue of square matrix. That's why we first of all define it. It's not a square matrix. We are not working with square matrix. Don't forget, we are not working on a square matrix, but we use that at the diagonal too. You will still be able, like this one now, if I find the transpose of this matrix, for example, if I say A transpose now, remember A transpose will be different from normal transpose. I can say 1, 2, 0, 2, 1. So by the time I find this one, what do you think I'm going to have now? Am I going to have the same dimension again?
No.
No. So definitely the rank will also will change in this case. So in this case now, R of A is 3. Then I will advise you, please, everybody, it's just an advice, it's not compulsory. Go to your material, look for some of those definitions there. Like I said, the one you can memorize them. The one you cannot memorize, make sure you write it out by yourself so that at the point of writing, you have idea of what is happening there. So in this case now, we can now use the method, the formula to solve it. Rank A plus nullity of A. We are looking for nullity of A. Our nullity of A in this case will now be nullity
5 minus 3
equals to n minus rank A.
Sir,
Yes.
please, I have a question. How did you get n to be equal to 5? Is it because the number of columns is 5?
Yes. So
okay, that n means the number of columns.
Yes, n means the number of columns. That's why they write it here. Is the domain. Remember when we did I explained domain and codomain for us. How many domain do we have in that? How many elements we have in that domain? The one we did the last time is 4. We have 1, 2, 3, 4 to map to the other codomain. So in this case, the dimension of in a layman language, we can call it column. That's why they explain it here. Dim column space of A. Please, let's take note of those definitions. They are very important. So at the end of the day, you have it to be 5 minus 3, which is equal to 2. Now, not all the time, nobody will be asking you all these elementary ones. They will ask you in algebraic manner, which you need to prove. And part of the algebraic manner is what we just show here. So please, let's take note of that. We are already overshoot our time.
So please, I have another question. I'm so sorry, please.
Go ahead.
You said the other time that you saw in some questions where in exam and in theorem we are writing.
You are writing.
So we are writing E exam, which comprises of. So is it? Will we be able to prove there also?
Come again, please. I can't hear you clearly.
You said the other time that you will be that you've seen some questions before that students have to prove one thing or the other. But since this course has to do with E exam, where we'll be writing objective and subjective questions. And so is it possible that we'll be asked to prove something there?
What? If if you are doing E exam.
Okay.
I understand what you are saying. Remember in mathematics, whether even from JAM, let's start from JAM. You are picking objective, right?
Yes, sir.
In JAM is objective. And if it is objective, let me stop sharing. If it is objective, we don't forget